Okay, you still have a week left on that homework assignment. Man, it really must be a doozy if I've given you so much time. We just finished quiz 4. Now today we're going to continue talking about the synthetic unit hydrograph, the Snyder method. We didn't quite finish that on Thursday, so I'll put the solution up and make sure we're all on the same page. It's largely just an empirical process, and so there's not a lot of tie-in to the fundamentals there other than the fundamentals of you need a unit hydrograph sometimes where you don't have measured values for. We're also going to talk about a procedure called S-hydrographs, and we'll get into that today. So the Snyder synthetic unit hydrograph. What we had was some relatively large watershed with an area of 5.42 miles squared. Main channel length is given, and so on. The process, I gave you a handout, right? So the handout had the step-by-step of what to do. So let me pull up, I think that the majority of you are getting pretty close to the end of that. What we are going to do is, first of all, find the synthetic unit hydrograph if you know your rainfall excess lasts an hour. And then what does the unit hydrograph look like if the storm duration is 30 minutes instead? So here was the handout that I had provided. Let's see if we can do a full screen view of that. All right. Now, I specify in the handout what the units are supposed to be for everything, and I didn't bring it with me, but there is a proof for why it's supposed to be 640 for the BG units, and like you can go through and look at CFS and square miles and lengths and everything, and the units kind of make sense in a way for these coefficients, but it all sort of falls apart when you start looking at the time to peak, because those are all just strictly empirical where the units don't really match up so well. Okay, so let's just double check some of the calculations you've done so far. Now, this first part A was where we're looking at a 1 hour duration of rainfall excess. And remember that that's different than a 1 hour duration of rainfall, because what we're saying is during a 1 hour period is when there's enough leftover precipitation that we've satisfied the abstractions and infiltration has been satisfied, so the time to ponding has already elapsed because now we're starting to have excess. And you don't begin having excess until after the abstractions are accomplished and until after the ponding has occurred. Okay, so raise your hand if for the T sub PR you got 3.928 hours. We on the same page so far with that? Good. All right. The QPR 551.9 CFS per inch. Okay, nodding heads is good. Now these parameters W50 and W75, just to take you back to what that's about, that's trying to find the width of the hydrograph so that we can know the overall duration from the beginning of the rainfall excess to when the peak flow comes back down to zero. So you use those factors to find these times. T sub B is the base time, the overall duration of the storm. And from the overall duration of the storm, we can calculate the time to peak. So once you have the width of it, the time to peak, the Q peak, then you can graph it. And here's what the graph ought to look like. So the overall T sub B is the 14.53 hours that we calculated. Time to peak is from the beginning of rainfall excess being measured until we see the peak. And the peak is going to be, for every inch of rainfall excess, there would be 551.9 CFS. Okay, so the part B of this is the same process, except for now we're going to let the T sub R, capital R, be 0.5 hours. So we want to find out how different does that unit hydrograph look if all of the rainfall excess happens in a half hour instead of an hour. And so I won't narrate through all the calculations. I'll just pause for a moment and let you copy down anything that you maybe didn't get to. But ultimately, what we want to do is compare the two hydrographs. And what we would hope to see, a sooner peak does happen. Instead of 4.4 hours, it's 4.0 hours. There's a slightly shorter storm duration, and the peak, instead of being 551.9 CFS, is 570 CFS per inch. So that same 1 inch of rainfall happens more quickly, then it's going to lead to a larger peak as well. So let me give you a moment to copy anything down that you might not have gotten yet on part B. Just pause the recording here. Okay, so that's the Snyder synthetic unit hydrograph, just using regional parameters and some physical data that can be gathered using GIS to estimate what the unit hydrograph might look like. So there is an in-between, because what we've talked about so far with unit hydrographs is the real unit hydrograph when you have observed physical data for a storm of a certain duration and you know what the response coming out of the watershed to that is. And then at the other end of the extreme is this completely synthetic method that just comes up with a triangular unit hydrograph, which is kind of weak in a way. I mean, it helps us to understand what the peak might be, but not the flow at other times other than the peak, not very accurately. So the middle ground is accomplished with a method called the S-hydrograph approach. And what that'll allow you to do is it'll allow you to take a unit hydrograph that has a certain duration, a certain rainfall excess duration, and convert it into a unit hydrograph of another duration. So let's say that there was a watershed that you've been studying and you had a really good two-hour storm, but you wanted to know what a 4-hour storm is going to look like in terms of the stream response in that same watershed. What this S-hydrographs method will allow you to do is convert the runoff hydrograph from a 2-hour rainfall excess to a 4-hour rainfall excess, or any duration that you're interested in. So you'd be given a beginning hydrograph, and what we do in order to come up with the different duration is we repeat the given hydrograph over and over and over again and come up with something called an S-curve. And what you can see is that the S-curve is the sum of these overlapping hydrographs where we've delayed them by the rainfall excess duration equivalent to the storm that caused the hydrograph to begin with. So if this was 2 hours of rainfall excess, then this T sub r here in our rainfall hydrograph is 2 hours wide. You can see that the peak is coming after that. But we assume that there's these repeating 2-hour storms back to back to back. And that's what would cause the S-curve. And through a procedure that we're going to go through in Excel, what we can do is convert it to the 4-hour duration by having these overlapping curves and then subtracting them out. All right, so here is our given rainfall, and let's start up Excel. Hopefully you got the message to bring your computer today. So this is a S-curve transformation of a unit. My typing is not on point. So we're changing here the duration of the rainfall excess from 2 hours to 4 hours. And the first thing that we want to have is a column that has our time in hours. So we'll just put in the given data off of this example. So some storm we have measured the runoff in 2-hour increments. So go down through 24 gets us to 0 again. And then here is the 2-hour unit hydrograph. And that's CFS per inch of rainfall excess. Okay, so once you get it on there, we're going to need to repeat this same hydrograph over and over again, but it's going to be delayed. So if we go back to what this looked like, so here's our original actual hydrograph. We want the same thing, we want it delayed by the duration of the storm. So we were told that this hydrograph is because we had a rainfall excess event of 2 hours. What that means is we want to take the same hydrograph, copy it, Control-C, and then paste it with a 2-hour lag. So you'll notice instead of the 0 runoff starting at hour 0, now I've got this lagged one starting at hour 2. I'm just going to call this like column number 1 of our additional hydrograph. And then in the second column, I'm going to do the same thing. I need to lag it by 2 hours to cause this third overlapping hydrograph. I guess you probably have an idea of where this is headed. For the third one, I'm going to lag it for, oh shoot, I'm going to lag it for another 2 hours, and again, and again, and again. And in fact, we need to do this quite a few times. So I'm going to make these columns a little bit narrower just so I don't run out of screen area. And I'm going to end up having 11 of these. And you know, there's nothing magic about 11. It could have been 12 or 13 or 100. But 11 will be enough as it ends up. So I'm going to continue to copy and paste these with a 2-hour delay. And then the S-curve, you can see from the figure on this slide, the S-curve is the sum of all of those overlapping hydrographs. So this next column is going to be the sum. And so this is the S-curve. So it'll be the sum of all of the columns to the left, excluding time. The actual runoff hydrograph and all of the lagged ones as well. All right, let me pause and give you a moment to make sure you've got all of that. Okay, now there's a really important check that we can put in place to make sure that this method is correct. And All we're going to be changing in this S-hydrograph is the duration that the rainfall excess occurred. We're not changing the amount of the rainfall excess. And what that means is that the volume of runoff should be the same, regardless of whether it's a 2-hour storm or a 4-hour storm. Because by definition, rainfall excess means that which wasn't infiltrated and wasn't intercepted. So we have the same amount of runoff depth, it's just occurring over a different duration. So one of the important checks that we can make is summing up the volume of runoff during both the 2-hour storm and the 4-hour storm. So let's put this first check and calculate the runoff volume for when the rainfall excess was occurring over a 2-hour duration. So runoff volume, this is going to be in cubic feet. Okay, so each one of these represents a 2-hour block. So to calculate the runoff volume, I'm going to, I think I can sum all of these up and then multiply that by 3,600 times 2, and then that will give me the runoff volume. Yeah. So it's essentially saying, assume that you have 69 CFS for 2 hours, and then assume that you have 143 CFS for 2 hours, and 328 CFS for 2 hours, and so on. So I've added them all up and multiplied them by the number of seconds in a 2-hour period. Okay, so that's 14,508,000 cubic feet. If we do this process correctly, then the 4-hour unit hydrograph we have at the end of it should give us the same volume. So it's a way for us to double check and make sure that our answer is correct. Okay, so we've got our S-curve, and now we're also going to create a lagged S-curve. Did it? Oh, yes, thanks for noticing that. Yeah, good call. Let me just move it over here. I'll just change the formula. I don't want to move it. That's better, right? Okay, good call, good catch, thank you. All right, so the next thing we're going to do is a lagged S-curve. And what we're supposed to do is take the same S-curve and lag it by the number of hours that we want the unit hydrograph to be equal to. So we're going to lag it by 4 hours because we want a 4-hour unit hydrograph. So lagged S-curve, it's lagged by 4 hours. So take the same one, and we're not going to paste it just the next one down. We're going to paste it the one after that because somehow I need to paste the numbers themselves, the values, instead of pasting the formula. You know how to do that, right? Paste the values rather than the formula. Because if the default paste is it's going to paste the sum, and so it would be like the sum of C through N. That's not what we want it to do. We want these very same numbers, but lagged, not 2 hours, but 4 hours. So that's why, normally here we were just going in 2-hour lags. This one is a 4-hour lag. Okay. So we've got our lagged S-curve. And then the lagged 4-hour hydrograph. Now we're just moving it up to the right time by subtracting the two. So it's going to be equals to, well, this, by the way, we need to put these zeros in here because there's no flow yet for the lagged S-curve. So now, this lagged 4-hour hydrograph, it's a subtraction. So I'll put in parentheses here, subtract the S-curve and the lagged S-curve. Okay. So equals the S-curve minus the lagged S-curve. And then drag that down and it's going to do something magical. Once it gets to 0, we can just fill in the rest, like these negative numbers here. Let's see, 20 is the last real value. Then from there it's just 0, 0, 0, 0, 0, 0. So this is why we didn't need to continue with additional columns, is eventually, since the S-curve ends, then the lagged S-curve doesn't need to continue any further as well. Now the problem with this, though, is that the volumes are wrong. So we've got the relative amounts correct at this point, but it would be too much volume if we just left it here. So there's one more step. And in the instructions here, it says we have to divide the result by T prime R divided by TR. So T prime here is the desired duration of 4 hours, and T sub R was the original duration for the rainfall excess of 2 hours. So we need to divide by 4 divided by 2. So we have to divide in half. So then our final here, the 4-hour unit hydrograph, is going to be these amounts divided by 2. And then once we get that, we'll check the volume to make sure that it is in fact the same runoff volume that it was before, but just delayed at different times. So the formula for checking the volume was the sum of all of these multiplied by 2 times 3,600. And the runoff volume is the same, 14,508,000 cubic feet. But if you look at the amounts, like the timing of it is delayed. So this was a unit hydrograph with a 2-hour rainfall excess, and the theory says that it's the same watershed. So, the slopes of the watershed didn't change, and the sinuosity of the streams and the stream density is the same. The roughness is the same. The only difference is the duration of the rainfall excess. Instead of 2 hours was 4 hours. And so the curves look pretty similar. The peak is slightly lower. Instead of 389 CFS, you'll notice now that that brings the peak down to 370 because the rainfall excess is over a larger period of time. Here, before, the peak occurred at hour 8. Now the peak is occurring at hour 10. And that makes sense because the rainfall excess is spread out over a longer duration. So both of the effects that we would expect, the delay of the peak and the peak being lower, both of those occur. So that's the S-hydrograph method, and I think that's one of the final components of the homework assignment that you've got due on Tuesday. It's just repeating that same process. I'll give you a moment to finalize your own spreadsheet. All right, so just to summarize the process here, we were given a unit hydrograph. We created this sequence of lagged, and so it was lagged 2 hours at a time because that was the original rainfall excess duration. If you had a rainfall excess duration before of 1 hour, then you need to lag it in 1 hour steps. Created the S-curve, and then you shift it by the amount T prime R, and that's the desired storm duration. So we wanted to find out what does the hydrograph look like for a 4 hour, and so that's why we lagged by 4 hours, is because the desired storm duration is T prime R. subtracted out the S-curve from the lagged S-curve, and then because the volume had doubled, we divided by the ratio of T prime R to T sub R. So the original duration was T sub R, T prime R is the desired. And you divide by that ratio, and then it brings the volumes back in line.